This is aniline. Aniline is really important in the dye industry, in the pharmaceutical industry, and lots of industries. And today we're going to talk a little bit about how we can make this important in the dye industry, but also how this can give us lots and lots of cool substitution products. As a reminder, in Lab 2, we actually did some research into converting an NO2 into an NH2. Hydrogen and palladium on carbon will do it, iron and acid, a couple other things. If I take this aniline and treat it with sodium nitrite in acid, so aqueous HCl, and I keep it cold at 0 C, I can get this diazonium ion, so actually an N2 there. Pretty dang good leaving group, but it is stable if it's on an aromatic ring and we keep it relatively cold. It'll hang around for a few minutes. The mechanism for this is rather lengthy, but we end up with nitrite gets protonated to nitrous acid. A nitrous acid is actually an electrophile, so my amine can attack that. I get a new NN bond. I can essentially lose water here via some proton exchange reactions. And then when water leaves, I get this thing, which if I add a proton and can remove water, takes me to this diazonium ion. Again, they're generally not stable, but if it's on a benzene ring and we keep it cold, it's relatively stable. So this intermediate diazonium ion can be converted into a lot of different things. And the mechanism for all these reactions I'm going to go through, the mechanisms change, and sometimes it's not really well known exactly how it goes, or it's much more complicated than this class is ready for. At a first level, you can kind of picture it as, oh, this is the greatest leaving group of all time. It leaves. I have phenyl plus. It's a great electrophile. Whatever nucleophile it wants is going to attack with it. We can kind of go with that, at least for this first one. So if I take this and add it, or just keep it in water and boil it, eventually I'm going to replace that N2 with an OH. I'm going to get a phenol. That's the only way I know of to actually put an OH on a ring like that, right? So that's a pretty useful thing to have. So again, in essentially one operation, I converted an NH2 into an OH, right? That's pretty useful. What else can I do? If I give this a weak reducing agent, and this H2PO2 is a really common one, hypophosphorus acid. The pH bond is really weak, and so I can actually reduce this down and put a carbon-hydrogen bond here, which you might think is a pretty dang expensive way to make benzene, right? So again, I'm converting an NH to just an H. That might be useful if I want a strong withdrawing group or a strong donating group to kind of direct some chemistry, and then I want that directing group to go away, right? That might be a useful trick for that. Copper salts seem to be really, really useful in these kinds of reactions. So copper chloride will give me a chlorine there. Copper bromide will give me a bromine there. And notice copper cyanide will actually add a cyanide to that ring. And hey-yo, carbon-carbon bond. Nice. Usually we call these Sandmeyer reactions. And again, the mechanism is a little bit complicated. It probably involves some kind of aryl copper species, maybe a radical in there. But in general, these reactions work pretty well. Lastly, I can put iodines on the ring. I don't actually even need copper for it. Just potassium iodide is pretty good for this reaction. And finally, if I heat it up with fluoroboric acid, HBF4, I can actually put a fluorine on the ring. You may have noticed the conspicuous absence of fluorine when we talked about adding chlorine and bromine and iodine in our halogenation video, because it don't work. Even if you could get your hands on difluorine, which I wouldn't recommend because it's nasty, that reaction doesn't work. And so this is one of the few effective ways to actually get a carbon-fluorine bond, which if you've looked at medicinal chemistry a little bit, that's actually a pretty common thing we'd like to have in drugs. So diazonium ions. We can get there from anilines. We can get anilines from nitro compounds. These things aren't the most stable thing in the world. I usually can't put it in a jar. But at 0 Celsius, it's stable enough for me to use it to do other stuff. I can make phenols from it. I can just get rid of the functional group and have a nitrogen or a hydrogen. I can add halogens, chlorine, bromine, iodine, even fluorine, and I can even add a cyanide, which would represent the formation of a new carbon-carbon bond, right? So lots of things I can get to it. It's kind of magic and kind of cool. Finally, I said that these diazonium ions were important in the dye industry, and they are, but not by any of those reactions that I just drew. So imagine we took this diazonium ion and we added more aniline to it, right? Or we only made a little bit of the diazonium. What might happen is that this is actually a good electrophile, a normal old electrophile, and this aniline can attack it. What do those arrows give me? After this attack and after it loses that extra hydrogen, what I end up with is another essentially electrophilic aromatic substitution. And this one is actually commercially available. So this is an azo dye. This group here, this NN double bond in the middle of a compound is called an azo linkage. And most artificial dyes are azo dyes, or at least the old-fashioned ones and the ones that we would rather not be eating too much of. But that look really pretty are generally azo dyes. What makes them colored is this electron delocalization throughout the system. Right? So these diazonium ions, usually we think of their chemistry as I'm going to pop off that N2 and add some other nucleophile, be it water or a halogen or cyanide. But with some nucleophiles, especially some aromatic nucleophiles like this, I can actually add into the nitro compound and get an azo dye complex.